Okay, so good day, everyone. So now let us discuss the topic for chapter 3, which is the strength analysis of reinforced concrete beams using NSCP 2001 and NSCP 2010. Okay, so we need to discuss the two codes since there are some variations on the constants and the factors that we need to use in our analysis. Now, later you will know some of the differences from the two codes. Okay, so we have here the analysis versus design. Okay, so we have two types of problems arise in the study of reinforced concrete. So first one is the analysis. Okay, so in the analysis, given a cross section, the concrete strength. Okay, so we have the cross section already. Okay, so we have the width and the height of the concrete, or the beam rather. Then we have the strength F prime C of the concrete. Then also we have the reinforcement size. Okay, it is already given, the diameter. Okay, diameter of the bar. Then we also know the location, either it is on the compression or the tension side. Then also the Fy, or the yield strength of the stirrups and the main bars. Then in here we are tasked to compute the resistance or the strength of the beam. So in the analysis, there should be one. Okay, take note, there should be one unique answer, because our beam has a specific strength or specific resistance on a particular loads. Okay, so we also have the design, wherein design given the factored design moment. Now, so this is mu. Okay, mu is given. Okay, so here it goes, mu. Then select a suitable cross section, including dimensions, concrete strength, reinforcement, and so on. So in design, there are many, okay, possible solutions. No? So it's up to you to decide what would be the dimension for B, what would be the B and H, and also the AS. Okay, so that's it for design. Then, although both types of problems are based on the same principles, the procedure is different in each case. So analysis is easier, okay, because all of the decisions concerning reinforcement, bar size, and so on have been made, and it is only necessary to apply the strength calculations principles determine the capacity of your beam. Design, on the other hand, involves the choice, of section dimensions, material strengths, and reinforcement placement to produce a cross section that can resist the moments, or the mu, due to factored loads. Okay, so those are the differences between analysis and design. So in design, it's quite challenging, since it's up to you. No, it's up to you as a structural designer on what would be the size of the beam, the size of your bar, the placement, how many bars that you will be using, the specific concrete strength, and the yield strength of your bar. Okay, so design methods. So we have two design methods. First one is the working stress design, or the allowable strength design, which is referred to as WSD. So the dead load and live loads to be supported, called working loads or service loads, were first estimated. Okay, so meaning these are unfactored loads. No? So then the members of the structure were proportioned so that stresses calculated by transform area did not exceed a certain permissible or allowable value. So we're already finished in discussing this one in chapter 2. Okay, then now in chapter 3 we will focus more on the ultimate strength design method, or make use of more rational approach, than WSD. Okay, so this is USD, guys, USD method. Okay, and uses a more realistic consideration of safety, which provides more economical. Okay, so strength design uses factored loads, factored loads as multiplier for service load, and will result to values referred as factored loads. So the members are then selected, so they will theoretically just fail under factored loads. Okay, so those are the differences for the two design methods. Okay, so 3.3 required strength and design strength. So the basic safety equation for structural element is that the reduced nominal strength should be greater than or equal to your factored loads effects. So meaning this is reduced, it is referred to as reduced normal strength, because you will be using a P factor, meaning that is the strength reduction factor. Okay, then you have a factored load, so this is the actual load. So this one, the nominal strength is the capacity, the capacity of your section. Okay, so meaning if we will convert it into an equation, so that would be P times R sub N should be greater than or equal to R sub U. Okay, so if we will consider a beam subject to bending or flexural stress, then MR will be converted into MN, then RU will be converted into MU. Okay, so PMN, so meaning the capacity of your beam should be greater than or equal to the factored loads, or the actual loads. So that is the required strength and the design strength. Okay, so 3.4 load factors and load combinations. So I think you're familiar already with this one, wherein factored loads are numbers that are multiplied to service loads in order to increase its estimated values applied to structures. So the loads are increased to take account some uncertainties involved in estimating their magnitudes. Okay, so at least you have a allowance for uncertainties. Okay, so that is one of the main purpose of having a load factors. Okay, so in NECP 2001, so required strength U to resist dead load and live load shall be equal to 1.4 dead load plus 1.7 live load. So just follow the pattern here. So this one, if it involves dead load, live load, and wind load. For this one, if it involves dead load and wind load only. Okay, then dead load, live load with earthquake loads, then dead load and earthquake loads. And this one is with earth pressure H. So this is the factor. So and just read some of the written concepts here now for load combinations. So how about for NECP 2010? So the ultimate strength design, or the required strength, shall be at least equal to the effects of factored loads in equation 409-1. So these are the factored loads involved in NECP 2010. So some of the differences is that for dead load and live load, so NECP 2010, wherein U is equal to 1.2 dead load plus 1.6 live load. So previously that is 1.7 dead load plus 1.4 dead load plus 1.7 live load. So it was reduced, no, in some certain values, no. And just read some of this one. If you wanted to have more load combinations, explanations about loads, so refer to chapter 2 of the NSCP code. Okay, so aside from the differences between the load combinations and load factors in NSCP 2010 and 2001, so there are differences as well in the strength reduction factors. So I already introduced this one earlier, that is the P factor. So these are numbers multiplied to nominal loads to decrease its value. Now that's why it is referred to as the reduction factors. No? So the decrease of value is take account for the uncertainties again. Aside from uncertainties, then the inaccuracies in the design equations, also approximations in analysis, then possible variations in dimensions of concrete sections and placement of reinforcement. Okay, so the importance of members in the structure of which they are part, and so on. Okay, so for NECP 2021, so the strength reduction factor P shall be as follows. Okay, so for flexure without axial, okay, so meaning if you will be analyzing a moment, no, so your reduction factor would be 0.9. Then for axial load and axial load with flexure, okay, so for load with flexure, both axial moment nominal strength shall be multiplied by appropriate single value of P. Okay, then axial tension and axial tension with flexure, that is 0.9 still. Then axial compression and axial compression with flexure. So members with spiral reinforcement. Okay, so I think this is for columns. Now for columns, guys, spiral. So that is for circular columns. Now you will know later uh, as we will discuss the column sections. Na. So for spiral, okay, with axial compression and axial compression with flexure, so that would be 0.75. Then for other reinforced members, so meaning, say for example, if your column is a square column, a rectangular column, so that is 0.7. Okay, so except that for low values of axial compression P shall be permitted to increase in accordance with the following provisions. So for members in which H does not exceed 415 MPa with symmetric reinforcement, and with H minus D prime minus DS over H not less than 0.7. So P shall be permitted to be increased linearly to 0.9 as VPN decreases from 0.10 F'C Ag to 0. Okay, and for other reinforcement, P shall be permitted to be increased linearly to 0.9 as VPN decreases from 0.10 F'C Ag or VPN wherever is smaller to 0. Okay, so more of that will be discussed in the column section, okay, or column design later. So for shear and torsion, now if we are involved with if we are dealing with shear and torsion, then the factor will be 0.85. So bearing on concrete, that is 0.7. Then post tension anchorage zones 0.85. Okay, so in seismic zone 4, strength reduction factor phi shall be given above except for the following. Okay, so for the shear reduction factor shall be 0.6 for design of shear walls, topping slabs that uses diaphragms over precast concrete members, and structural framing members with the exemption of joints. So if their nominal strength, the shear strength is less than the shear corresponding to development of their nominal flexural strength. Okay, so reinforcement used for diaphragm cords or collectors placed and topping slabs over precast concrete members shall be designed using strength reduction factor 0.6. Okay, then strength reduction factor for flexure, compression, shear, and bearing of structural plain concrete. Okay, structural plain concrete shall be 0.65. Okay, for maybe for conservative, no, for a conservative design, no, for the plain concrete. Okay, so for 2010, the strength reduction factor for tension controlled sections, so you will know later what is tension controlled section, that is 0.9. Then compression controlled sections, meaning this is for the columns, no, if spiral, that is 0.75. Then for other reinforcements, say you have square or rectangular columns, so that is 0.65. Okay, so I think there's difference already there for the other reinforcement, no. So earlier in 2001, that is 0.7. So for the new codes 2010, so that would be 0.65 already. No, it was reduced to 0.65. Okay, for sections in which the net tensile strength E sub T is between the limits for compression controlled and tension controlled sections, phi shall be permitted to be linearly increased from that for compression controlled sections to 0.9 as E sub T increase from the compression strain limit to 0.005. Okay, so you will know later of this. Okay, then for shear intorsion, that is 0.75. Let us check if there's a difference there. Okay, so from 0.85 down to 0.65, 0.75 rather. Okay, for bearing on concrete, 0.65 into 2010. Then from 2001, that is 0.7. Okay, so for post tension anchorage zone, which is 0.65, okay, so same, 85 rather, so they have the same value in NCP 2001. For strut and ties model, that is 0.65, 75 rather. Okay, so these are some of the factors, no, for the flexural sections in pre-tension members. Okay, so hopefully you will be familiarizing these factors, guys, no, because we will be dealing with this one in our designs later on. Okay, so beam formulas and derivations. So test of reinforced concrete beams confirm that strains vary in proportion to distances from the neutral axis, even on the tension side and even near ultimate loads. Compression stresses vary approximately in a straight line under the maximum stress equals about 0.5 F'C. This is not the case, however, after the stress go higher. So when the ultimate load is reached, then the strain and stress variations are approximately as shown in figure 3.3. No, so this one here. So figure 3.3, this is the actual and equivalent stress diagram. Okay, so wherein, so this is your beam section. Then if a certain beam, say for this one, simply supported beam, with certain loads. No, so as the loads goes higher, then uh, the strain and stress variations are approximately varies into this particular stress diagram here. Now, so that is the stress that were experienced by your beam cross section. Okay, so Whitney replaced no the curved stress block at actual stress distribution with an equivalent rectangular block of intensity 0.65 F'C in the depth of compression block, which is A is equal to beta 1 times C, now as shown in 3.3. So the area of the rectangular block shall equal that of the curved stress block, and the centroids of the two blocks shall coincide. So sufficient test results are available for concrete beams to provide the depths of the equivalent rectangular stress block. So this is applicable for both NSCP 2010 and 2001. Okay, so Whitney is quite wise, no? Since if we will try to analyze the stress, no? If we try to analyze this stress here with a curve, so this is quite difficult not to analyze. So what he did is he converted the curved stress block into a rectangular stress block, no, to make the analysis more easier, no. So from F prime C, no, the stress that is F prime C, down to 0.85 F prime C. So there's a reduction of 0.15, and from the C, C distance, which is the distance of the neutral axis to the extreme tension fiber. So he created a depth, a compression stress depth, which is equal to A. Okay, so this one now will be the stress diagram here with curve stress will be equated now to this particular stress diagram here, a rectangular compression block. Okay, okay, so now for NACP 2001, factor beta 1 shall be taken as 0.85 for concrete strengths F prime C up to and including 30 MPa. Okay, so take note of that one. For strengths above 30 MPa, so beta 1 shall be reduced continuously at a rate of 0.05 for each 7 MPa of strength excess of 30 MPa, but beta 1 shall not be taken less than 0.65. Okay, so that is the range. No, the range is 0.85 to 0.65 up to 0.85. Okay, so for 2010, beta 1 shall be taken as 0.65 for concrete strength F prime C 4, now for 17 MPa up to 28 MPa only, no? So 2001 is up to 30 MPa, no? So it was reduced now to 28 MPa in NACP 2010. Okay, so for strengths above 28 MPa, so beta 1 shall be reduced linearly at a rate of 0.05 for each 7 MPa of the strength excess of 28 MPa. So again, it should not be taken less than 0.65. Okay, so now to derive the equation, so we equate forces horizontal as shown in figure 3.4. So we can derive the formula of the depth of the compression block A. Okay, so let us discuss the figure 3.4, which is the stress and strain distribution of the beam. Okay, so earlier, so we have this beam section already. Now we have this beam section. Okay, so we have this beam section. Then this is now the stress diagram, now as formulated by Whitney. So this is 0.85 F'C with a compression block. Then this is now the strain diagram, wherein the strain at the compression side is 0.003. This one with C distance here. Then we have the strain of the tension side. Now from the neutral axis, say this is your neutral axis, so the distance there is D minus C. Okay, so now we may convert it into a force, no? So this one here, for the stress diagram, we could create an internal couple there, no? So we will convert this stress into a force, no? Into an internal force for let us say for the compression part. So if we will draw it in 3D, guys, so this is now the 3D drawing. So this is the rectangular, and this one here, so this is the rectangular stress block compression for specifically. So we will convert it. Okay, so we will convert it into a force wherein that is equal to C is equal to 0.85 F prime C AB. So that is the rectangular here, guys, no? So I think you're familiar with area pressure, no, from your statics, no? So this is the area A times B, then multiply it with 0.85 F prime C. Okay, to have a force, no? Say for example, say since 0.85 F prime C, say this is in MPa. If we will try to have a unit analysis, that is Newton per mm squared, then B is mm, then A is mm. Okay, so Newton per mm squared, then multiplied with mm, then mm times mm. So this will be equal to Newton alone, no? So this is now in Newton, no, if you will using an SI unit. Okay, so the same with the tension side, where these are the stresses for your bars. So this one here, this one is AS, no? Area of the steel. So area of the steel will be multiplied to your yield strength Fy. So you have the tension force here, that is equal to AS times Fy. Okay, so we have this internal couple now, which is C is equal to 0.85 F prime C. Then for the tension is equal to AS times Fy. Then that could be equal to Mn, no? So this is since C is acting at the center of your compression block, so therefore this is A over 2. This is also A over 2. So that is D minus A over 2. Okay, so in order to derive this formula here, so I think what uses here is summation of forces X, no? Or so if you have this x-axis and y-axis here, so these are the forces involved, T and C. Okay, so that is equal to C is equal to T, wherein C is 0.85 F prime C AB, then T is AS times Fy. Okay, so therefore your formula for your depth of compression block is equal to AS times Fy over 0.85 F prime C times B, or the width of your beam. Okay, so aside from having the basic formula, which is beta 1 times C, take note that the C value is not equal to this C here, no? Since C is distance from the uh, compression extreme compression fiber to your neutral axis, while the C here is the force, no, the internal force coming from your compression block. Okay, then how about for the ratio of area of steel to the effective area, or we denote that one as our steel ratio, no, rho. No, our rho is equal to AS over BD, no, AS over BD. So that is the ratio of area of steel over effective area of your concrete. Okay, so this one. Then substituting the steel ratio from the equation of the depth of compression block, so it becomes this one now. Okay, so if we will substitute it here, no? So assuming the section is tension controlled, the steel will yield first before the concrete reaches its ultimate strength. So the value of the nominal moment for rectangular beams can be written as this one. Okay, again this one is coming from the internal couple diagram that we have here, this one. Okay, so if we sum up moment at the tension side is equal to 0, then we have, I know, not equal to 0, equal to mn. Okay, so wherein mn, guys, will be equal to 0.85 f prime c ab then times d minus a over 2. Okay, while if you sum up moment at the compression side, which is equal to mn, then mn would be equal to as f prime c then times d minus a over 2. Okay, so just simply draw, guys, the diagram, no, for you to easily derive the formulas given below. Okay, so this one here. Okay, so just simply substitute the value of T and the value of C, or the equation of T and C. Then the usable flexural strength. Okay, so since we are trying to analyze the section to a factored loads, no, since we are dealing with USD already, the ultimate strength design, then therefore this nominal strength here, or this is nominal, no? nominal moment capacity. So this should be converted to a design, no, to design moment capacity. Now if we say design moment capacity, then we will be using a strength reduction factor already, no? Phi. Okay, so that will now become phi mn, no? Phi mn is equal to, so just simply multiply phi as well to your as times fy times d minus a over 2, and also to your phi times 0.85 f prime c ab then times d minus a over 2. Okay, so those are the formulas, no? Okay, now let's proceed to the balance, tension control, and compression control sections. Okay, so let us discuss first the balance design, or the balance condition. So for balance strain conditions exist at the cross section when tension reinforcement reaches the strain corresponding to its specific yield strain Fy, just as concrete in compression reaches its assumed ultimate strain of 0.003 in accordance to NCP 2010. So balance condition is a design so proportioned that it divides two different types of failure modes, which are brittle and ductile failure mode. Okay, so if we try to illustrate that one, so you can see in figure 3.4, the strain diagram at balance condition. So if we have this NA here, so since that is so balanced, then your concrete, no, if your concrete reaches the strain which is equal to 0.003, so your strain at the tension reinforcement which is equal to Fy over Es will be reached as well. So meaning sabay, no, sabay sila mag-reach guys into their limits. So meaning if your concrete cracks or your concrete fails, then your steel also fails, no? Or meaning if your steel yields, then your concrete will also crack, no? So it will happen at the same time. Okay, so that is the balance condition. No, for how about for the tension controlled or the ductile or the under reinforced condition. Okay, so sections are tension controlled if the net tension strain in the extreme tension steel E sub T is equal to or greater than 0.005 when the concrete in compression reaches its assumed strain limit of 0.003. So sections with E sub T between compression controlled strain limit and 0.005 constitute a transition region between compression controlled and tension controlled sections. Okay, so we will know more of that later. So a beam section with lesser steel than that of balance condition will fail in ductile behavior. So the decrease of tensile steel will result to higher location of Na, which will cause the concrete to reach a strain of 0.003 after steel yields. So the increase of load at this section will cause the steel to stretch at a considerable amount. So the strain of steel will continue to increase, resulting to large deflections. However, as the stress in the steel reaches Fy, so the stress will not increase. So as the load further increases, the compression concrete fails as a secondary effect. So the type of failure is desirable, no, because of adequate warning of the users. So meaning guys, out of the three, no, or maybe let me discuss first compression, no, for us to at least conclude what is the desirable method or the desirable option for the design of our beam. So either it is balance, either it is tension, or either it is compression. So let me discuss first compression control. So this is brittle or the over reinforced design, no? So sections are compression controlled if the net tensile strain E sub D is equal to or less than compression controlled strain limit when the concrete in compression reaches its assumed strain limit of 0.003. So the compression controlled strain limit is the net tensile strain in the reinforcement at balanced strain condition. So for grade 415 reinforcement and for all pre-stressed reinforcement, it shall be permitted to set the compression controlled strain limit equal to 0.002. This is with accordance to NCP 2010 with section 410.3. So a beam section with more steel required than that of balance condition will fail in brittle behavior. So para mapulbo, no? Para mapulbo siya. So the increase of tensile steel will result to lower location of Na, that will cause the concrete to reach a strain of 0.003 before steel yields. Again, this is undesirable. Failure occurs since failure will be initiated by sudden crushing of the compressive concrete. Okay, so normally guys, tension control, compression control, and balance condition are the new terms, the new terms that were used in a design. So from, I think in NSCP 2001, so they uses the word over reinforced, under reinforced, and also balance were not changed. Now balance design or balance condition. So the most desirable, guys, the most desirable design is the under reinforced design, under reinforced design, or the tension control design. So it was mentioned already here that it is desirable, since there is an adequate warning of the users, so meaning it manifests cracks, so ang pinapaintindi dito, guys, is your beam will give you a warning through cracks, through deflections, through large deflections. So at least you are warned already that the section is not adequate anymore to carry additional loads. Okay, so also in tension control, in simple explanation for tension control, so steel yields first before concrete cracks, or that is or that was explained already here, so which caused the concrete to reach strain of 0.3 after steel yields. Okay, so steel yields first before concrete cracks. For balance condition, steel yields at the same time. So that is the keyword here. Steel yields at the same time concrete cracks, and this is quite dangerous. This is dangerous, because there would be sudden collapse of the section without any notice, without any warning, without any indication of cracks, without any indication of deflections. So this is quite dangerous. The same with the over reinforced, design, or with the compression control, wherein concrete cracks before steel yields, so that's why it is considered as brittle design, because your concrete will brittle first, before steel yields, before your steel will fail. Okay, so that was mentioned also here, that the concrete will reach a strain of 0.003 before steel yields. Okay, so I hope it's clear already, that the most desirable design would be the tension control design, or the under reinforced design, or the ductile design. Okay, so hopefully it's clear already, if we try to design a particular section specifically for beams. Okay, so now, to derive expressions for balance condition, so we apply similar triangles, and knowing that E, or the modulus of elasticity of steel, is 200,000 MPa. So similar triangles, or we'll be using this one here, guys, no? The strain diagram of the balance condition, this one here. Okay, so I think this is C, then this is D minus C. Okay, so similar triangles lang, guys. Then we have here C, which is C over 0.003, then dt minus C over Fy over 200,000. So therefore the value of C, or the equation for C in balance, take note, this is in balance condition, which is equal to 600 dt over 600 plus Fy. Okay, so for the equation A, no, that we have derived earlier, we can get beta 1 CB is equal to steel ratio, which is rho B, then Fy times D over 0.85 F prime C. So substituting the equation of CB, we can obtain the equation of steel ratio at balance condition, or this is balance condition, guys, rho B, which is equal to 0.85 F prime C beta 1 over Fy times 600 over 600 plus Fy. Okay, take note, this is for balance condition alone. Okay, so now, since the desirable method is ductile under reinforced or the tension control, then we need to know the ductility requirement, no, that were stated on both 2001 and 2010 NSCP codes. Okay, so for NSCP 2001, for flexural members and for members subject to combined flexure and compressive action load, when the design action load strength VPN is less than the smaller of 0.10 F'Ag or VPB, so the ratio of reinforcement rho provided shall not exceed 0.75 of the ratio of rho B, that would produce balanced strain condition for the section under flexure without action load. So for members with compression reinforcement, so the condition of rho B equalized by compression reinforcement need not be reduced by 0.75 factor. Okay, so that is for the 2001 ductility requirement. Okay, so I think rho is 0.75 of rho balance, no, that is the ductility requirement for 2001 NCP code, no, as stated here. Okay, so the ratio of reinforcement, which is the rho, shall not exceed, okay, or we shall say this is less than or equal to 0.75 of rho balance, no, so that is for that particular condition. For 2010 NCP, for non-pre-stress flexural members and non-pre-stress members with factored axial compressive load less than 0.10 F'Ag, we'll be using strain here, no, E sub T. Okay, so strain T at the nominal strength shall not be less than 0.004. Okay, because all values of E sub Y for current reinforcing steel bars are less than 0.04. The ductility requirements ensures a tension controlled flexural member. Okay, So this is 2010 is more easier to understand, no? So since uh, the the difference here is that in 2001 we are using the steel ratio, while for 2010 we are now using the strain, okay, for the ductility requirement. Okay, then now for minimum reinforcement of flexural members, no? So this is AS. I think this is AS minimum. Okay. So for both 2001 and 2010, so at every section of a flexural member where tensile reinforcement is required by analysis, except as provided in sections, these sections here, AS provided shall not be less than the given equations. Okay, first is AS minimum is equal to square root of f prime c over 4 fy, but not less than, no, but not less than 1.4 over fy times bw times d. Okay, so I think if we will try to again recall that our steel ratio is equal to AS over BD, right? BWD. So if we will multiply that one, we have AS is equal to rho, then BW times D. So meaning, if this is BW, then this is BW, then therefore this equation here, then we have AS minimum, no? AS minimum. So we have rho minimum. Okay, so rho min would be equal to square root of f prime c, okay, f prime c over 4 fy, but this should not be less than, or meaning this should be greater than, no, greater than 1.4 over fy. So this is also equal to rho minimum. So we have two equations for rho min. Okay, so just try to meet the conditions, guys, no, and not less than. So that one there. So for a statically determinative section with flange in tension, the area AS min shall be equal to or greater than the smaller value given either by AS min square root of f prime c over 2 fy bw. Okay, so take note, this is for T section with flange in tension, so meaning, guys, the reinforcement is at the top, not the top portion. Okay, this is your T beam, then you have your reinforcement here, no, because this is in tension. Okay, or equation 410-3, except that bw is replaced by 2w, or the width of the flange, whichever is small. Okay, so the requirements of section 410.6.1 and 410.6.2 need not be applied if at any section AS provided is at least 1/3 greater than the required by the analysis. Okay, so those are the some of the concepts that you need to know before we analyze a singly reinforced beam, a doubly reinforced beam, and also a T beam. Okay, so I think before we proceed with analysis of singly reinforced beam, so I need to cut first the discussion here. Okay, so thank you, guys, for listening, and keep safe, everyone.